Right. Good morning, everybody. Hope everybody's doing okay. Welcome to our next lesson here in Calculus BC. Right. We are in Unit 8. We have learned a bunch of stuff so far. We learned about this idea of parametric equations and how to do some calculus with that. Now we're going to lead into vectors with calculus. But you're going to see the setup for vectors is very similar to the setup for parametrics. So before we jump into vectors, let's do a parametrics equation. Or yeah, for one. Okay, so it says an object moving along a curve in the xy plane has position x of t, y of t at time t greater than or equal to 0 with d of x over dt equaling this and dy over dt equaling this. Okay? At time t equals 0, so initial time t equals 0, we have an initial position. X equals 13, y equals 15. And at time equals 2, the object at point P, is at point P with an x coordinate of 3. Okay, so that's kind of helpful. Find the y coordinate of P. Okay, find the y coordinate. Well, we know the x coordinate. We want to know the y coordinate of P. Okay. First of all, this is definitely a calc active problem. Just want to clarify that. And if we want to know the y coordinate, I want us to think back to last semester. How do I find a new value given an initial value? So initially speaking here, at time equals 0, we have a y value of 5. Okay? So I'm going to say 5 plus. Now, if I want to know my new value at time equals 2, that is an accumulation, right? It is a change in value from time equals 0 to time equals 2. So how we talk about that change is integral 0 to 2. Okay? Well, what position are we talking about changing? We're talking about changing the y position, dy over dt. So that is ln 1 plus t minus 4 to the 4th dt. Okay? That will tell me the change in my y position from 0 to 2. We add it to our initial position at 5. Now, this is definitely a calc active problem. This is something that we can't do on our own, by hand at least. So the answer I'm getting is 13.671. All right, then it says write an equation for the line tangent to the curve at point P. Okay, so maybe I'll try to squeeze part C right here. Remember, if you ever want to do a tangent line, you need 3 things. So I never want you to overcomplicate it, even though we're in a different type of equation. We still need an x value, a y value, and a slope. Okay, so we got the x and the y value, right? So at P, we know the x value is 3 and the y value is, I was going to say 5, I apologize. It's not 5, it is 13.671. Right, I mean, we were told the x value, we just found the y value. The only other thing we need is the slope at P. So in this case, we need the slope, dy over dx, at the point of P, and that is at time equals 2. So I'll put t equals 2 here. Now again, this is calc active, so we'll do this in the calculator. But all that is dy divided by dx with a t, with the 2 plugged in. So that's ln of 1 plus t minus 4 to the 4th divided by 12t minus 3t squared with a 2 plugged in for t, right? And I'm getting in the calculator 0.236. So my tangent line is going to be y minus the y value, or y minus 13.671, equals my x value, or I'm sorry, my slope, which was 0.236 x minus 3. Okay? So that's how you do tangent line, right? And then lastly, in part C, it says, and I'm going to try to squeeze this in right here. It's calc active, so I'm not going to need much math here. It says, for what values of t, if any, is the object at rest? And explain your reasoning. So your reasoning's pretty simple. We know that we're at rest when v of t equals 0. Okay? We're at rest when v of t equals 0, or when the derivative dy of x, I guess I should call it dy of x, or dy over dx, when that is equal to 0, right? That's when we're at rest. So we know with a fraction, so this is my dy over dx, we know with a fraction that happens when the top part equals 0. So really the only math behind this is to figure out where ln of 1 plus t minus 4 to the 4th of x equals 0. Again, calc active, t minus 4 right here. Can't really tell. I don't really know if we can solve that by hand. I think it's going to actually end up being 4 because it's the ln of 1 that equals 0. I think t is going to end up equaling 4. So let's double check that in the calculator real quick. And yeah, that's equal to 4. Okay. All right, now another cool little problem with this, and then we'll move on to vectors. I just thought this was a fun little parametric equation. Is it says find the area enclosed by the curve t squared minus 2t and the square root of t and the y-axis. Okay, so I encourage you to graph this right now. I encourage you to try to go to your calculator and graph this, or if you want, do the long way. You know, figure out your x and your y points, and then plot them. You know, if we have that whatever t equals, we can plot that, no problem. Maybe start off with t equals 0. But when I graphed it, I got this general looking shape right here. Okay, so I just wanted to kind of go ahead and tell you that. So I want to know, okay, so I want to find the area enclosed by this curve and the y-axis. So here's the y-axis, and the curve would be this right here. Okay. If you were to graph this, the function is going in this direction right here. Okay, it's going in that direction right there. So if I want to find the area enclosed by the graph, I need to have kind of like my starting point and then kind of my ending point here for t. T would be doing this. Okay, so I need to have like a t start and kind of like a t end in order to do this. Okay, so we start here, we end here, and it keeps going. So what t value is going to enclose this area? Well, what's going to happen is like what they have in common is that at both of these points, the position for x is equal to 0. So if we take our x position and set it equal to 0, I can solve for those 2 points. Right? We get t equals 0 and t equals 2. Okay. And then we know the setup for this from our previous lesson. We know that the setup for this is going to be the integral 0 to 2 of our y equation, so the square root of t, multiplied by our dx, or the derivative of our x equation, so 2t minus 2 dt. And you can do this in the calculator, or you can do this on your own, but it ends up being 0.75. Okay, so there's an okay recap of yesterday's stuff with parametrics, just a little piece of it, but let's move on to vectors. Okay. All right. Now, vectors are going to look very similar to how we set up a parametric equation. Okay, they're very, very similar. And in fact, some teachers don't even really teach vectors that much, or the difference between vectors and parametrics, but I'm going to try to highlight that a little bit because there is different calculus involved with it. Okay. All right, first of all, vectors differ from parametrics because vectors are used to indicate a quantity that has a magnitude and a direction. A magnitude is like a length of a vector. Okay? And a direction, well, we know what a direction is. It's a certain way you're going, and we notate that using theta. Okay? So we have a length and a theta. So for instance, like right here, here's a vector given us, vector AB. So like how we can notate that, we would say like, we would use notation AB, and we put a little line above it, okay? So like, I mean, let's say for instance, okay, we have this vector, I'm gonna draw a little coordinate plane here, okay? The angle measurement always comes from what we call the initial side right here, which is the positive x-axis. Okay, so the angle formed, all right, from this vector is all, it starts with the initial side and it ends on the vector side, right? So that angle right there would represent the direction, okay? So again, this is kind of called my initial side, and we're going to end at something called this is called the terminal side, and that's my actual vector. Okay. Now, with a vector, this is a similar part to parametrics. A vector is going to have like a horizontal component and a vertical component. Okay. I mean, let's say for example, the horizontal component was like a length of 3, and the vertical component was a length of 2. Okay. Well, how we would describe this vector is very similar to how you would see parametrics. Instead of like, it's like almost like a little V bracket, and you're going to put your x direction first, and then your y direction. So this right here, this like V looking thing, I mean these little weird little brackets things, with the x component and the y component, that defines this vector. Okay, now how it differs from parametric is it's not a point, but it's talking about like this length right here. It's describing a length right here, and a vector from point A to point B. Okay. So, again, let me just kind of write that down real quick, just so we can see the form of a vector. So, vector form. All right, you got to have 2 points. Okay. A, and then with the A, we have some initial, position, and B, kind of where it ends. Okay. That's a B right there. Now we define that vector from point A to point B is we put A, B with a little line above it, like I said. And the vector has this little brackets. The x component is the change in x, right? It's the difference from x of B to x of A. And the y value is the difference from y of B to y of A, like my delta y, my change in y. Okay? Order matters here, people. You want to make sure that you do your ending point B, subtract your starting point A to get the correct position for your vector. Okay? Now, a vector, all right, you need 2 coordinate points to define a vector. And this is kind of, I'm trying to define the difference between vectors and parametrics here. With a vector, you have one movement. Okay, one movement. Okay, like here's point A, we move to point B. A to B, right? That is a vector. And with that movement, you have 2 things, right? You have a direction, which is an angle, and you have a magnitude, which is a length. Okay? Now, it's just going to look similar to how a parametric works. I mean, you can even see it. We define it with x and y parts. But with parametrics, there's a parameter involved. Okay? There's a parameter involved, and it models movement. So it models movement over time, over some parametric some parameter. Usually it's time. Okay, and I got a good visual later on that kind of shows the difference between the two as well. All right. So with the time I have remaining, I'm going to try to just do a few examples of different things and try to re-explain things the best I can. I'm trying to give you a good exposure to what vectors are. And honestly, the calculus behind vectors, I think, are actually a lot easier than the calculus behind parametrics. All right. Now, okay, so we talked about vectors. We talked about how it has a direction, which is just an angle. But we also talked about how it has a magnitude, which is a length. The magnitude notation looks like this. Now, I know that looks like the absolute value symbol, because it really kind of is, and we'll touch more on that when we get later on in our lessons. But like, let's say I want to know the length of a vector. We're going to call that vector A. Okay, now vector A can be written as maybe a horizontal component. We'll just call that A1, and a vertical component, we'll call that A2, right? This is the change in X, and this is the change in Y, okay? And honestly, we can also have more than one component. We can have a Z component as well. I mean, we could also say that we have A1, A2, or A3, a change in X, a change in Y, and a change in Z if we have like a third dimension. But regardless, however many we have, the magnitude is just going to be the square root of A1 squared plus A2 squared. And if we have that third component, then it's going to be plus A3 squared, depending on however many you have. It's just Pythagorean theorem. It's just distance formula, right? This is the change in X, so that's X2 minus X1. This is the change in Y, and possibly a change in Z if we have that third component. So magnitude is nothing more than the distance formula. Okay? All right, now also with vectors, there's something else we need to know. There's three special vectors. Okay, there's three special vectors. They're called standard, or what I'd say mostly is unit vectors. Unit vectors. Now, this is a strange thing, honestly, for us. Sometimes it doesn't make sense in calculus because we don't have as much application with unit vectors. But sometimes we want to write a vector in like separate forms. Sometimes we want to write it in its X component only, plus its Y component only, plus its Z component only. Okay? So we call the I vector, the I unit vector, that's the one for X's. So we would say 1, 0, 0. The one for our Y values would be 0, 1, 0, and for our Z values is 0, 0, 1. So let me show you how we can separate and create a sum of unit vectors. We're going to call it a sum of unit vectors, because sometimes we're going to have to write our vectors in unit vector form. So for example, I got 1, -2, and 6. So this is telling me like the change or my position or where I'm at in the X, Y, and Z directions. Okay. So right now this is something called component form. Right? This is the form we're used to seeing it in when it just writes it as its different components in the X, Y, and Z fashion. But there is a way to write it as a sum of unit vectors. Okay? This is your I, this is your J, and this is your K. It's pretty simple. All you're going to do is write it as 1I, or you can just write it as I. And make sure you put a little line above it to make sure you signify that that is a vector, that is something that's important. So we got 1I minus 2J plus 6K. Okay? This right here is a sum of unit vectors, because you can simplify this down and it's going to lead you back to component form. Like this is the same thing as saying 1, 0, 0, minus 2, 0, 1, 0, plus 6, 0, 0, 1. And if you were to distribute these values through and combine like terms, you would be left with a component form. Now, sometimes they like to write it this way because of for operation's sakes, and there's a last example where we can do something like that. But for now, all I want you to be able to do is just write it as a sum of unit vectors. Okay? All right, so come on. All right, I really like this slide because it's helping us kind of see the difference, I think, between vectors and parametrics. Okay. So we're going to use the form R of t. Okay? We're going to use the form R of t to define our vectors equation. Okay, we're going to use R of t. Now, this is telling me a position in the x, the y, and the z directions. Okay? Now, you could write this in a sum of unit vectors if you really want to, and we might have to do that. So let's just go ahead and write that down. Plus g of t times j plus h of t times k. Now, that's something that we could do. But here's a good visual that I really want us to be able to maybe help us distinguish between parametrics and velocity, or parametrics and vector. Okay. The pink line here, which I'm highlighting again in red, this is something that you might see for a path of a particle, and it has a specific direction to it, right? It has a specific direction to it. So this looks very similar to a parametric equation, right? Parametric. So the thing about a parametrics is it's going to describe the motion or the path of a particle given some parameter t, right? Now, what a vector does, and the difference between a parametric and a vector, is a parametric has like a direction and an angle associated with a vector, with a particle. So let's say that this initial condition or this initial position is the coordinate like middle axis point, the origin. Okay, let's say it's the origin. Let's say it's at this point 0, 0, 0. Well, for instance, one vector on this path of the particle would be from this point to say like right here. Okay, this is a vector. This is telling me a difference between a start to an end. So I have a length. I also have a direction and angle measurement to get to this point. Okay, here's another vector right here. Here's another vector right here. Here's another vector right here. So I can have the sum of all these vectors, all these individual vectors, create this same looking path. But it's just defining it in a different way. Okay? So with a vector, it all has an origin points, and we have these lines with links and stuff like that. The path itself can be defined parametrically or with a sum of all of these vectors. Okay? A good way that I've heard people kind of distinguish between parametrics and vectors, besides the difference of a magnitude and a length, is they said, okay, visualize like you are holding a flashlight, and you're standing in one spot, and you're taking that flashlight and you're running it across the wall. Well, the path that little light that you're making, that path that it's following, that would be like a parametric equation. The line of the light from your flashlight, all those lines are making that path. And all those lines that you're making as you're moving that flashlight, those are vectors. Okay? And that's kind of the difference between the two. Now, I know that's kind of probably not the best example in the world, but hopefully you kind of visualize that a little bit. So you're going to see a lot of similarities between how we set up vectors and how we set up parametrics, but the math is just done a little bit differently. Okay? Now I'm at 25 minutes and I'm not doing a bit of good getting to any calculus with this today. It's mostly just review. But one thing that I would like to talk about, I'm going to end on this slide right here. This is the last time we're on. We can cross this out, and we can cross this out. One thing I want us to understand is that we have R of t back here being our, almost like our position function for velocity, telling us the position of our particle or whatever in vector form. We can also have a velocity vector. We're going to call that v vector of t. Okay? And honestly, this is the easiest thing in the world. It's the derivative of our function that we just talked about before. It's just a derivative of each of the components. So honestly, all it is f prime of t, g prime of t, and h prime of t. And that's it. Okay? And it's probably the easiest thing in the world to compute because we don't have to do anything fancy with it. It's just three separate equations that we're going to take the derivative of. And if you want to know what the acceleration vector is, it's the second derivative of my initial position vector. So this will be like f double prime of t, g double prime of t, and h double prime of t. Okay. Last thing I want to say before I'm going to end, and we'll just do all the math, I guess, together. This is just kind of a little reminder of what vectors are, but the calculus, I promise you, is nothing terrible. Okay. So the last thing I'm going to say is that we can talk about the speed. All right, the speed of a vector is nothing more than the magnitude or the length. We know that means length of the velocity. So you're going to see that absolute value of v of t symbol that we saw before, but instead of putting a there or my position, we're going to put v of t. And notice that it's the same exact formula for magnitude as we talked about before, but instead of f and g and h, it's f prime, g prime, and h prime. Okay. All right, well, I tried to give you, as best I could, a little recap of what vectors are, how they compare to parametrics. And then when we meet together, we'll be able to actually jump into doing some problems. So example 1, 2, 3, and 4. So I have 4 examples. Okay? So, good job, guys. I appreciate everything that y'all do. And I hope y'all have a fantastic